the company behind Elasticsearch, the product, and I compiled a list of little less known features of Elasticsearch, along with some use cases, how they can be used. So hopefully it will not be boring even for people who are fairly familiar with Elasticsearch. But just sort of to make everything right, we will start with the basics anyway. So first, what do you expect? Sort of the first feature that you expect from something that's called Elasticsearch is a search. So how does search work? And we'll from that see how we derive other different functionalities. So search is not a very new problem. It has been around for a long time. And it hasn't changed much. We pretty much use the same principles as were used in the year 1230, where a first sort of search index has been composed by some monks. And we use the same data structure to this day. The data structure is inverted index. It is inverted because it uses the insides of the value to point back to the document. So in our case, we have 4 files. We have file 1, 2, 3, and 4. And we have five different words that can occur in these documents, in these files. So first to note is that both the words and the files occur in a sorted fashion. So when I want to search, when I want to locate something that mentions Flask, I can do it using binary search on the list of words, so it is very effective. And then what I get essentially is a list of files in our case. In a case of a book, it would be a list of pages where this word actually occurs. So this is the very same data structure that you're used to from a book. At the end of the book, you will see a list of names and a list of pages that you can use to look things up. So the looking up thing is just that simple. So if we're looking for a document that mentions both Python and Django, all we need to do is locate those 2 lines that corresponds to those 2 terms, those 2 words, and just take the list of those files, so file 2 and file 4, file 1, 2, and 3, and just merge them together. And because we're using the AND operation, so any file that occurs in both of those lists, that is our result. So a super simple operation. We look up a word in a sorted dictionary. This part here is called the dictionary. And then we take the lists, technically it's called posting list, and we merge them together. And again, because they're sorted, we can do that very effectively. It has also one other interesting property. I don't care where the lists actually came from. Once I have this list and this list, I can merge them. I can merge more than 2. I can merge any number. I can also merge these lists even if they came from a different index. So if I have index per field and I have multiple fields, I can use multiple indices during a simple query. So this translates that as opposed to the more traditional data stores like SQL and everything, we're not limited to the number of indices that we can use per a single query, because we can use all of them at the same time. The idea is just to get as many posting lists as necessary and then just merge them. And because they're sorted, the merging operation is very, very effective. So this is how search works in 10 seconds, the briefest overview of inverted index and how it works. But we can do more with it. The one fun part that we can do with an inverted index is we can power an inverted search. So what an inverted search is, in terms of Elasticsearch, this feature is called the percolator. And it is exactly that. It is a reverse search. Normally, you put documents into your Elasticsearch cluster, into your data store. And then you run individual queries. And that is fine, and it is a very useful feature, but sometimes you want the opposite. Sometimes you want to index all your queries, and then essentially run the documents and get back all the queries that would otherwise have matched on the document. Especially on an example. So imagine that you have a CMS, you have a blog, and you have different categories in your blog. Like this blog post is about programming, and etc., etc. And your CMS allows you to define the category dynamically. So you just define essentially a search pattern, and all the blog posts that match that search pattern will be in that category. So it is very trivial to create a listing for that category. You just run the search and you display the results. That's your dynamic category. It is, however, a much harder problem than to decide what categories is a given blog post in. Because, especially for these dynamic ones, there is no way how to do it unless you run all the queries across all the documents and try to somehow match it up. And then everything changes and you need to redo this. That is where percolation comes in, where you can actually index all these queries that define the dynamic categories, and then you show it a blog post and it will automatically tell you right away, hey, I belong into these 5 dynamic categories. So that's one use case. Another use case is, for example, for alerting. So you're indexing some events, and let's say you're indexing stock prices, and you want to be alerted when the stock price of Elastic, the company, goes above 2 cents. So you just create a percolator, you just index the query, and before you index the stock price, you ask Elasticsearch to do the percolation. So that's alerting. Some people use it for live search. If you've ever seen a search on a website, if not, I'm sorry, this must all sound like gibberish. If you've ever seen a search on a website, and then you look through the results and suddenly pops back that there are 5 new results, that's what we call live search. And it's very easily doable with the percolator. Because you run your search, and at that time, you also register that very same search as a percolator. And then you get alerts as new documents come in that, hey, you should actually do a push request to this browser because he's still looking at the results. And thus you can sort of very automatically have this functionality without having to invest into it heavily. But what we're going to look at, which is the less obvious use cases, is classification. So essentially to discover more information about our documents. So first one that we'll look into is Geo Classification. Imagine that you have events, you index events, and each event has an address, has a geo point. But it only has a geo point. It doesn't tell you which country it is in or which city. So the simplest thing you can do is you can somehow acquire a list of shapes for all the cities in your country or in the world. There aren't that many cities you can actually afford to do that. And then you create a percolator for each. So this is a percolator for the city of Warsaw. It is called the city of Warsaw, and it's essentially a query that if we just ran this query in the regular way, it would give us all the events that are happening in Warsaw within the shape that you have stored somewhere in your index that identifies the city of Warsaw. If we use this as a percolator and we show it a document, it can tell us whether or not this event happens in the city of Warsaw. That on its own, it's not very impressive. But you can have hundreds and thousands of these percolators for each city in the world. So essentially, if you show it a document, it will tell you which city it is actually in. So that's Geo Classification. If you have a query that matches some area, you can turn that around and sort of identify the area where something is. The other use case is language detection. I use Polish here because Polish is very distinctive. But it is very true for most languages in the world that they have several words that only occur in that language and in no other. So it is fairly easy to construct a query that will have a long list of words, and it's essentially asking if there are at least 4 of these words. We can safely say that this document is actually in Polish. So it is a very sort of naive approach to language detection, but it actually works if you're able to identify those words. In Polish, it's very easy, but for other languages, it might be a little bit difficult. But still, this is a valid approach, and you can, if you have these lists for many different languages, you can create a percolator for each. And then again, you can show it a document, and it will tell you, yeah, I'm fairly sure that this is in Polish. Or you can get even multiple results, that this is in French and also in English. At that point, it's probably in Canada. So you can use it to detect languages. So this is how you actually create the percolators. Those are just queries that are indexed into Elasticsearch, the same way you would index a document. You're just using the HTTP REST API, you just put into your index, there's a special reserved type called .percolator, and you just name it, name your percolator. And then when you actually have the document, you can just say, this is in that index, it's of the type conference, and I want to run percolation. And what you get back is the list of percolators that have actually matched on this document. So you show it a document about the conference with the location and everything, and you get back the city, the language, let's say the topic, because again, it's fairly easy to construct a search query that will identify a meetup or an event that has to deal with Python. It probably will contain words like Python and Django and programming and .py and all these different things that if you find them, chances are good that it is actually about Python. So you can dynamically detect sort of the topics, the categories. So this is the percolation. This is the first sort of a little hidden feature of Elasticsearch that not many people use or know about. It is something that scales fairly well. We have seen people doing millions of these. We even know of some people running Elasticsearch just because of percolation. They don't actually store any data in it, yet they have a cluster of 20 nodes because they want to be able to do percolation on millions of queries very, very quickly. So, any questions for percolation? Going once, going twice, moving on. So sort of the next area, and we'll sort of be stuck with this until the end, is the concept of relevancy. Because that's really what distinguishes a full text search engine versus some other more traditional data store. We not only tell you that a document matched your query, we will tell you how well it matched. And we will tell you fairly well if you're dealing with text. There are several ways how we do that, but the core of it is something called TF-IDF. It's a formula, or it's actually an input to a formula where TF stands for term frequency. Essentially, how many times have we found this word in this document? And then there's IDF, which is inverse document frequency, which is essentially just saying how many documents contain this word. And these two together will give us an idea about how good a match this is. Because if we found a word twice, but it is in every single document out there, that's not really relevant. That doesn't mean much. But if we found a word even once, and it only occurs in 1% of our documents, that actually means something. That means much more. So that's actually what this stands for. This is the TF, and this is actually the IDF. And we throw in a logarithm just for good measure because it makes the numbers look better. So that's the core of the formula. And you can see here. This is the actual formula that's being used inside of the scene, which we'll not go into. If somebody's interested, we can talk about this afterwards. But these two things combined work very well for text. And if you don't know anything else about your but oftentimes you do know something about your data. Imagine that you run a website that has questions and answers primarily used by programmers. Let's call it like buffer overflow or something. So you can ask a question and you can get responses. And you have information, who is asking the question, who is giving the responses, the answers, and also people as they go by, as they come in from Google, they can say, yeah, this was a good question, and this was a good answer. So you have information from the users that actually tell you that this is a good answer. At that point, it would be prudent to actually use that information. So if you then search, it would be nice to not only use the text relevancy, so how well does the question describe what I typed in, but also use how good a question it is. And here comes the problem, because if you sort by the quality, by the user contributed number, you completely miss out on the relevancy. So if there is a question that is very long, so there's a lot of words, and it is very highly rated, it will almost always be on top. And there's nothing you can do. If you discard the popularity, you might have a question that describes the problem very well, but actually is rubbish because people have determined that it is. So what you want is for a way to combine these two numbers. And we'll see how we can do that. So that's sort of the first use case here, when you have some insight into what constitutes a good document. The other one might be where a document might lose relevancy, for example, over time, or with distance from a geolocation. So you can say that ideally it was published today. It's okay if it was published yesterday, but the further it is in the past, the less relevant it probably is. So we supply several functions that look like this, that actually implement this sort of behavior. You say that ideally I want it to be around the age of 40. And as further away as it gets from that, it should be less relevant. And obviously you can combine all of these things. So in Elasticsearch, it's a specific type of query called a function store. And what we do here is we're looking for a hotel. We're looking for a hotel that has a Grand Hotel in its name. And we have several other categories or several other qualities we want it to have. For example, if the room that I'm looking for has a balcony, add 2 to the score. If it should also be located in central London, within 1 kilometer of central London. The further away that it gets from that, it should not be. It should still be included, but it should not be at the top. It should be lower down on the result list. There's also the popularity of the hotel that we should take into account, the way I just described. And finally, throw in some random numbers for good measure. And those random numbers are there actually for a reason, because a lot of times people are a little wary when they always see the same results. So we just added a little randomness, and that gives them a chance to sort of discover new things that might otherwise be a little hidden. And now we're done. Now all we need to do is fill with all these little numbers. For example, popularity. Do we just take the value? Do we multiply it by 1.270? Or the which factor for the facilities that I prefer? Should it be 2, 3, 2.5? What is a good number? How should I combine these individual results? Should I discard the score from this, or should I just combine it? Should I add them together? Should I multiply them? There's a lot of things that go into this. If I'm super OCD, I can actually just replace all of this and just write a script that will do all this and actually calculate it exactly as I want. So this is sort of a way how to use the relevancy and add more stuff into it. Don't just rely on the text match, on the number of words and the rarity of the words. Use the information that you have from your domain. You know which hotel is good and which isn't because you have all the reviews. You know which answer is good because you have the karma of the user and you have the individual votes for the question and the answer. Use that. Otherwise, you're missing out on a lot of opportunity to make your search a lot better. So, relevancy. Does it make sense? Any questions there? No? Good. Either I've completely lost you or I've actually made myself clear. There's a question. So the question is if it's possible to add custom weights to all these different aspects. Yes, absolutely. There's a parameter called weight. Just add it there. It will work. Okay. So moving on. Another feature that is used a lot with Elasticsearch is aggregations. And aggregations, as they are fairly boring. Sure, they produce good pictures, but this is just essentially just counting stuff. Any data store worth its bits can do this if it's one of its descriptions. So with Elasticsearch, you can create aggregations like this and then visualize them. And there's only one particular thing how we differ a little bit. Whenever you do aggregations, the way to think about what you're actually doing is that you're dividing your data into groups. We call those groups buckets. And then within each group, within each bucket, you ask for an aggregation. Let's say for just the number of documents that fell into that one bucket, or for an average of a field. So in this case, we create a bucket per country. Within each of those buckets, we create a bucket whether the user has been signed in or not. This is some data from like visitors of a web page or something. And for each of those two sub-buckets, whether the user has been signed in or not, we create another bucket for the browser that they use. So immediately in one pass over the data, we can visualize something like this. When we have this many countries, and we can immediately see sort of the discrepancies. We can see them because we are humans. We are essentially pattern recognizing machines. You just take one look at it and you immediately know that these two are super different. You can immediately look into this and see that there's a gap here that probably shouldn't be there, and there's something worth discovering. And that is very important. But it is kind of boring. So what can we do that is past sort of the counting aggregations? Well, we are a search engine, right? So we have all this information about that we use to calculate the relevancy. So I'll show an example of how we can use all that to drive recommendations. So imagine that we have two users that bought some products. So we just create a document. We create a document for each user, and there's a list of products that he bought as individual terms, as individual words. And we'll do analysis on this. We want to look for recommendations. Based on what I bought, or based on what I like, what should I buy or like next? What would you recommend me? So the first kind of approach is, hey, we just get all the users that liked some of the same things and get the most popular artists that they listen to or products that they bought, without those that you've already listened to or already bought. And this is a very simple approach, but it doesn't really work much, because popular doesn't mean it's relevant. For example, if I ask you all, what is the website that you go to the most? The answer is probably going to be Google. That is absolutely not relevant at all. Everybody goes to Google. Not interesting. What is interesting, however, if I ask you here in the room, is that somewhere in the top 5 or top 10 there'll be GitHub. And that is a very good information. Because if I ask 1,000 people on the streets, not many people will even know that GitHub exists. So that is good information. That would be good recommendation if someone new came into this room. So how do we get there? As it turns out, it's fairly easy. Observe. Here there's terms. Here's their significant terms. That's it. And this is actually our aggregation that takes all this into account. Because we have all the statistics. We use them to calculate relevancy. That's why I've been describing all the formulas. Not because I think math is exciting, but because we need it here. We can actually use the score, we can use the statistics we have about the individual terms, about the individual words, to determine which ones are significant and which ones are not. So this is just looking for the strong recommendations. Essentially, if we were to visualize it, we have 3 concepts that are linked somehow. And this sort of algorithm or this type of aggregation allows us to determine which ones are useful and which ones are useless. It is obviously not perfect, and it will not beat Amazon's recommendations. They put a lot more work into it. But it will sure as hell beat the most naive approach, and it is actually a very good starting point. It is essentially a way how we can figure out the meaningful connections. What we like to say that we are looking for the uncommonly common. So, in other words, what is common for our group that is very uncommon outside of this group? That will be the GitHub example. Another place where you can use this is if you're trying to develop the trending functionality that Twitter has, for example. Just create one aggregation that will create buckets for each time period. Let's say a bucket for each day. There's a simple aggregation that does that. It's called the day histogram. And then within each of those buckets, you can ask for the significant terms, which will give you the words, not the most popular words in that bucket, but the words that are more popular in that one bucket, in that one day, compared to the background, compared to the regular Twitter chatter. So essentially, what is trending? What is suddenly gone up? What hasn't been up before, maybe not after, but it is specific for this topic. So this is the way how to identify meaningful connections. And it is a way how we look at the world. This is the way how we humans perceive it. We immediately focus on the uncommonly common. And this is one way how to replicate this with Elasticsearch, with computers, fairly easily. You don't have to be, deal with machine learning, and you don't have to know how to install a special Python library that can help you. You can just ask Elasticsearch to do a lot of the work for you. So another example, sort of more complex one, is we can use the same approach to find meaningful connections in Wikipedia. And I have this slide here mostly because I've done this exercise, and it's very fascinating what you can learn. If you put in two completely different pages, you can find connections between those 2 pages. But if you use this approach compared to just look at the common element, you can only go through the meaningful connections. Otherwise, you'll end up with links like, yeah, all those 2 people visited the United States at some point. So there'll be a link to the United States, and both of them will link it. That's not interesting, because so many people point to that one page that it loses its relevance. It's not a meaningful connection. So you can, again, use this approach. You can use the statement terms as sort of the one step in your graph algorithm to discover the meaningful connections from concept A to concept B. Well, in this case, the connection will be super small, but you get it. So, just to reiterate, like when you put these concepts together, so the aggregations, the bucketing, and when you take advantage of the relevancy of the mechanism that we have below that, you get a lot more out of it than just the pure information of how common is this number and what is the average of these two fields. Sure, there are good use cases for that, but sometimes you want more. Okay. So, are you tired, or can we still do a bonus chapter? Who wants a bonus chapter? Okay. So, when we do geo searches, how does this work? So imagine that you're searching for two shapes and how they intersect. So how this works in the background is we overlay the shape, the polygon, over a grid, and we essentially index every single cell that this polygon touches. And because of the cells are identified with names, with hashes, we now have a list of words, and we already know what to do with the list of words. We are a full-text search engine. Give us a list of words and we can do crazy things. So that's how it works. The problem is that the geo queries that we have, they have no relevance because they just look for matches, and there's no good way how to determine what is a better match than anything else. So if you have a shape for a continent, a country, a city, a street, and you ask for a shape of a house, you will get back all of these shapes, and with no concept of which one is more specific, which one is more relevant than the others. So there is no relevant difference between a continent and a city street. And that's not good. So we can sort of see already a pattern that we have here. We need to somehow make it special. The easiest way is, instead of encoding all the cells here, we always encode just 1,000 or any n. No matter how big the shape is, we would always index the same number of cells. And then when we look for something in there, we can just count the number of matches of the individual cells. And we can say that, yeah, if more cells have matched, then it is more relevant shape. Because in our example, when we have 1,000 cells representing a street and we're looking for a house, the house will probably have at least 100 of those shapes inside its shape. When we're looking at the continent, there'll be one at most. So not very relevant match. So this is how sort of you can introduce the concept of relevancy and the concept of the quality of the match to a problem that seemingly doesn't happen. You can use the same approach for ranges. Let's say that you have a website for hotels and you have the availability of a room. Again, if you want to find something, you can just say, hey, I have a date range, but I'll just index always just 4 days, no matter how long the range is. And then when you search for the range, the ones that will be on top will be those where the range is actually most close to the one that you search for. Any numerical range or anything like that will do, and this approach will actually help you. So this has been the bonus chapter, and overall my talk about the more interesting and more involved features of Elasticsearch, the features that actually let you get the benefits that are fairly unique to a search engine that no other data store can give you, because it actually uses sort of the default feature set of search engine and all the tools that we had to have internally because we are a search engine. So, any questions?
Is there any way how to retrieve those significant terms? How to, for example, I have a document, I want to know what are the most significant terms from the Elastic point of view?
Yes, Yes, you can very easily just ask for the term vector for that given field, or you can just create a bucket that contains just one this document and ask for the significant terms. That's the simplest solution. Any other questions? Okay, if you come up with any, I'll be around to come around me and ask me any questions, and thank you for having me.